All right, so here we are in the example section for section 6.1 about the definitions and basic calculus of inverse functions. So we're going to work through a couple of examples to illustrate some of the technique. The first thing we'll do is actually just compute an inverse. So we'll do a spot check using something called the horizontal line test to make sure that a function is one-to-one. And then after we do that, we will use the method of switching the variables and solving in order to find what an expression for the inverse should be. And then we will actually verify that the functions that we found are inverses. So let's begin with the function y is equal to the cube of x plus 1. So the first thing I want to do is I want to verify that y has an inverse. So you can use algebra to do this, or you can do a quick check using the horizontal line test. So what the horizontal line test gives you is a quick way of looking at a graph and identifying if that graph is one-to-one. If every line that you draw through the graph horizontally only crosses at one time, then that means that when you reflect that the reflection will be a function because it will pass the vertical line test. So if it only crosses through once for every single value that you write down, every line, every horizontal line that you put through it, then each x is associated to one individual y value. And each y only comes from one x, and that means the inverse will exist. So the answer I'm going to write is yes by the horizontal line test. Okay, step 2 is we're going to try to write down the formula for the inverse. So I'm going to start with y is equal to x to the third plus 1, and now I'm just going to do some algebra. Y minus 1 is equal to x to the third. The cube root of y minus 1 is equal to x. And then the last step is to swap the role of x and y so that I get a function. F of x is equal to the cube root of x minus 1. After all, if I don't swap the x and y, then that means I haven't done anything except reproduce the original function again. It's the swap of x and y that creates the inverse. So this is swap x with y to get the inverse. Now let's verify that these things are inverses. F and g are inverses if f of g of x is just equal to x. So what we've got written down right now is that f of x was equal to x to the third plus 1. And we're writing down that we think that the inverse of f is equal to the cube root of x minus 1. So easy enough to check. F of f inverse of x is equal to f of the cube root of x minus 1. And that means everywhere I see an x in this equation, I'm going to replace by this input right here. That gets me the cube root of x minus 1 cubed plus 1, which is x minus 1 plus 1, which is x. So that means that f of f inverse of x gets you x, and that means that you're looking at inverse functions. Okay, so we verified that the formula that we got out is actually an inverse. So the next exercise is going to be an illustration of the fact that sometimes we can calculate derivatives of inverses even when we can't find the inverse itself. So the particular function that we're going to look at is f of x is equal to 2x plus the cosine of x. And that's not a function we can find the inverse of because there's no way we're going to be able to get the x that's outside of the cosine and the x that's inside the cosine together. This is a transcendental equation. Okay? But we can still compute problems like this. Find f inverse prime of 1. So the big deal with this is that we're computing information about f inverse without knowing f inverse. So thematically, we are computing information about f inverse without a formula for f inverse. Because I can't undo this equation. This cannot be solved for x. So how are we going to do that? We want to use the formula f inverse prime of 1 must be equal to 1 over f prime of f inverse of 1. Okay, so this still begs the question how we find f inverse of 1. And in this particular case, that means that we're looking for an x so that f of x is equal to 1. So this particular problem we're going to do by inspection. What we were being tasked with finding was f inverse prime of 1, and I know that that's equal to 1 over f prime of f inverse of 1. So at least I need to know f inverse at one value. That could be approximated numerically or by inspection if you have an easy enough formula. So remember that f inverse of 1 is equal to x if f of x is equal to 1. And I know the formula for f because it's 2x plus the cosine of x. And this is true when x is equal to 0. Okay, so 0, 1 is the point on f, and that must mean that 1, 0 is the point on f inverse. And that means I can take this and say that f inverse prime of 1 is equal to 1 over f prime of 0. And now I just need to know what f prime of 0 is. Okay, well, if f is equal to 2x plus the cosine of x, then f prime is equal to 2 minus the sine of x. And that means that f prime of 0 is just 2. So this is equal to 1 over 2. So as long as I had information about f inverse at a single point, I can recover information about the derivative without knowing the formula. This is more useful than it looks because often you can numerically approximate what the values of f inverse should be. But approximating a point estimation for f inverse is not enough for you to be able to reconstruct the graph to get the derivative. Okay, so that's basically the two types of exercises that you're going to see in this section. And if you have trouble with either one of these, then let me know and we can do some more examples. All right, see you for logarithms.